Again, welcome to CS 113, Mathematical Structure for Computer Science, also known as Discrete Mathematics. In these lectures, we are going to continue with the Boolean algebra, and here we are going to discuss about representing Boolean function. So our main objective is how to find the sum of product, expansions, and also the functional completeness. So let's start with an example here. This is a sum of product expansion. The example given here is said we should find Boolean expression that represent the function f with three variables x, y, z. So f at x, y, z. And also g function at x, y, z in table 1. So this table is given to us, and we can see the three variables x, y, and z in the first, second, and third column. Then we have two functions. The first function is f, which is in the fourth column, and the second function is g. So each function have three variables, function f and g, based on the question x, y, z. And now the question says we should find a Boolean expression that will represent the function f at x, y, z, and also g at x, y, z. So to represent f, we need the one term x, y, invert, and z. In order to get the function of a sum of product, we have to have the function f column, which is right now I'm doing the f function first. When we look at the f function, anywhere we have 1, we are going to write the expression down, which we call the sum of product expression. So when you look at function f, we have only 1, which is in the third row. Again, you follow my cursor. The first row is 0, second row is 0, the third row is 1. The rest are 0. So when I look at the third row 0, when x is 1, we represent x as x, the variable as x. When x is 0, we represent the variable as invert of x. So which means here we have f function 1, again the third row, x is 1, so we have x, and y is 0, so it will be y invert, z is 1. So our sum of product expression here will be only 1, x, y invert, and z, because we have only 1. The rest is 0. Now, for example, if we have 2 1s, which we are going to see in G, that's where the concept of a sum of products will come in, because our expression will be product. Now, if I have 2 or more expressions, then I will add it together. So that's the concept of a sum of products. So our final solution for function f at x, y, z will be x, y invert, and z. Y is y invert because y is 0. X is 1, z is 1, so we have x and z. But y is 0, so it will be y invert. So we can see the solution here. Here they say to represent f, we need the one term x, y invert, z, because the expression has the value of 1. When x equal to z, which is equal to 1, and y is 0. So when we look where the function have 1, which is the f function, we can see that x is 1, z is 1, but y is 0. So that's why the term will be x, y invert, z. So that's the solution. Now, when we see at G, the G will give us the more solution that makes the concept of a sum of products more understandable. So when we look at the fifth column, which is the function G, in the second row, we have 1. And when we look at x, y, z in the second row, x is 1, so we have x, y is 1, so we have y, but z is 0. So the term will be x, y, z invert. But again, we have another one, which will be our 7th row. 1, 2, 3, 4, 5, 6, or 6 row. So in the 6th row, we have 1. But at that very row 1, x is 0, so we get x invert. Y is 1, so we get y. Then z is 0, so we get z invert. So our final solution will be x, y, z invert plus x invert, y, and z invert. So this gave us again the sum of product expansion. So that's the solution. We'll look at the sub 2, and we say the answer will be x, y, z invert plus x invert, y, z invert, because this expression has a value 1 when x is 1, y is 1, and z is 0. And also when x is 0, z is 0, and y is 1. So when we look at the G column, we have 2 1s in the 2nd row and the 6th row. The 2nd row, x is 1, y is 1, z is 0. So we have x, y, z invert plus the 6th row will be x is 0, y is 1, z is 0. So it will be x invert, y, z invert. So we can see from this expression is what? The sum of 2 products. So that's the whole concept of a sum of product expansion. Here we say the general principle is that each combination of values of the variables for which the function has the value 1 requires a term in the Boolean sum, that is the Boolean product of the variables or their complement. So we can have a question that, again, a truth table will be given to us. The output of the function will be given to us. Then based on the output of the function, we can again write the expression for sum of products. Again, the process is wherever we have a 1, output 1 for the function, we write the expression down. Now, if the variables can be any letter. Here we are using x, y, z. If the variables represent 0, then it will be the variable invert. So if x is 0, then it's x invert. If x is 1, then it's x. Then we use that to write our expression. So the definition said a literal is a Boolean variable or its complement. So a mean term of the Boolean variable x1, x2, and Sn is a Boolean product of y1, y2 up to yn, where again xi equal to yi, or we can have yi equal to si invent, complement or invent. So hence a mean term is a product of n literals with 1 literal for each, again, variable. So the mean term y1, y2 up to yn has a value 1 if and only if each si is 1. And this occurs if and only if si is 1 when yi equal to si and also si equal to 0. So the definition of a sum of product expansion is the sum of midterms that represent a function is called a sum of product expansion, or the disjunctive normal form of the Boolean function. And again, we're going to do one more example here. So for example, they say we should find the sum of product expansion for the following function. F at x, y, z, the answer is s plus y, z invert. So sometimes a question will be given. You see, the first example we already have the 0, 1, 0, 1 for the function already. So they don't need to give us the expression. But in our final exams, we may have a question like this. The truth table is not given, but the expression of the function is given. So based on the expression of the function, we can develop or we can create our truth table. And from the truth table, anywhere the function is 1, we can write the expression of the sum of product expansion. So here we have 3 variables, so we know the possible combination for a truth table three variables will be 2 to the power 3, which is 8. So I come down here, we have x, y, z in our table 2. The possible combination again is 8. So we start with 111, 110, 101, 100, 011, 010, 001, 000. So right now I have my possible 8 combination of the 3 variables input. So when I look at my expression, I have x plus y multiplied by z invert. So if I like, I can find x plus y first. So that's the 4th column, x plus y. 1 plus 1 is 1, 1 plus 1 is 1, 1 plus 0 is 1 again, 1 plus 0 is 1 again, then 0 plus 1 is 1, 0 plus 1 is 1, then 0 plus 0 is 0, another 0 plus 0 is 0. Again, I'm finding the s plus 1. So if s is 0, y is 0, then s plus y will be 0. If either of them is 1, then the answer will be 1. Now I know that the expression is s plus y times z invert. So I'll look for z invert also. So anywhere z is 1, z invert will be 0. So 1 is 0, 0 is 1, 1 is 0 again, 0 is 1, 1 is 0, 0 is 1, 1 is 0, 0 is 1. So we have z invert now. Now the expression is what? X plus y times z invert. So I'm going to multiply the 4th and 5th column together. X plus y times z invert. And anywhere I see 0, 0 or 1, 0, the answer is 0. We only get 1 when both of the terms is 1. So 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. 0 times 1 is 0. So again, in the first example, the expression was not given. The reason why, because the output of the function already is given. In this example, the truth table was not given. The expression is given. So if we have the expression, we can again develop the output, the truth table and the output of the function. So right now we have the output of the function. Here we have 3 ones. So we are going to write down our sum of products. Again, the question said, find the sum of product expansion. So the second row, I have 1. So which means S is 1, Y is 1, Z is 0. So my first sum of product, the term which we call the mean term, will be SY Z invert. Z invert because Z is 0. And SY is 1, 1. So you can see the answer here. We have SY Z invert. Plus, we have a second 1 in the 4th column. In that column, X is 1, Y is 0, Z is 0. So the term will be X, Y invert, Z invert. So here we have plus X, Y invert, Z invert in our solution at the bottom of the slide where my cursor is. Then the last one will be the 6th row. We have 1. And at that section, X is 0. So we have X invert, Y is 1. So we have Y. Z is 0. So Z invert. So our answer will be X invert, Y, and Z invert. And that's what we have here. So our total solution for the sum of the product expansion will be X, Y, Z invert plus S, Y invert, Z invert plus S invert, Y, and Z invert. We have 3 mean terms here. Why? Because we have 3, 1 output for the function. Also, we can find the sum of product expansion using the Boolean identities. So we, again, in our questions, we may say, a question may say, maybe find the sum of product expansion using Boolean identity, then you have to use Boolean identity. Or using the truth table, then we have to use the truth table. As far as the expression is given to us, we can use the Boolean identities to find the sum of product expansion. So let's see the same example. We have f at x, y, z equal to x plus y times z invert. So the first thing is, this is why we call the expansion, sum of product expansion. This expression is given to us, we have to expand it to get sum of product. So you can see that if I have something like this, x plus y, parenthesis times z invert, the first thing I have to do is the distributive law. I want to open the parenthesis. So I'll get x z invert plus y z invert. Z invert times s plus z invert times y. Now, when I reach here, I know I'm looking for 3 terms. So we decided to use the identity law, which we are going to add 1 to each. So we know S1 Z invert plus 1 Y Z invert. Based on the identity law, we can use the unit property by looking at X1 Z invert. Remember what 1 is. 1 is the same as Y plus Y invert. And that's what I'm missing here because I have X Z invert. So y plus y invert times x z invert is the same as x z invert because y plus y invert is 1. And we call this the unit property. In the second term, I'm missing x. So I'll use s plus x invert, which is the same as 1, times y z invert. Now we are going to open the expression using distributive law again. So we get x, y times z invert. It's like x z invert times y. Then x z invert times y invert. So we have s y z invert plus x y invert and z invert. The same thing, we have y z invert times x. So we get s y z invert. Then we have y z invert times s invert. So this time we get s invert y z invert. Again, this is distributive property. We multiply the terms outside the parentheses to each term in the parentheses. So finally, we have 3 terms here. We have x, y, z invert plus x, y invert, z invert plus s, y, z invert plus s invert, y, z invert. So our final solution will be x, y, z invert, we write it down. Then x, y invert, z invert, we write it down. Then here we have x, y, z invert plus s invert, y invert. Using the indefinite law, we get x, y, s, y, and z invert. So that will be our final solution. And we can see it's the same as using the truth table also. So next we move to the functional completeness. Here we say because every Boolean function can be represented using Boolean operators, such as the product, which normally is the period in the middle, period, or the plus, or the invert or complement. Again, because every Boolean function can be represented using the Boolean operators, plus, product, and complement, we say that the set product plus is functionally complete. So if I have a set, product, and complement, it's functionally complete since s plus y is equal to s invert times y invert or invert. And this is using the Morgan theorem concept, s plus y. Now, if I use the Morgan here, what will happen? I'll get s invert and invert. Product invert will give me plus. So plus y invert in invert. Invert and invert, 2 invert will cancel itself. So we get back to s plus y. The same thing applies to the set, plus, and complement. It's functionally complete since sy is the same as saying that s invert plus y invert or invert. If I use the Morgan theorem, I'll get s invert, plus will be product times y invert, invert. And again, 2 invert will give me, will cancel each other and we get y. Same thing applies to s. So which means our answer will be S times Y. So this is the concept again of functionally complete. The Boolean operators are, in Boolean operators, we don't have no division, just multiplication and addition. We don't have subtraction. Multiplication, addition, then complement. And actually, when we start the logic gate, which will be our next lecture, multiplication will represent AND gate, addition represent OR gate, and the complement will represent NOT gate. So we also have the NAND operator denoted by a vertical line. This is defined by 1 NAND 1 is equal to 0. So you can see the concept of NAND is like not AND. We know that 1 times 1 is 1. Not 1 is 0. Times is the same as AND gate or AND operator. And we may discuss this more in the next lecture. So we can see that 1 NAND 0 will give me 1. Why? Because 1 times 0 is 0. Not 0 is 1. So even 0 times 0 is 0. Not 0 again is 1. So with the NAND operator, it represents not AND. AND is multiplication. So when you multiply, you invert it. So not AND means not product or complement of product. Also, we have a NOR. NOR means not or. So if I have 0 plus 0, the answer is 0, then not 0 is 1. 1 plus 0 is 1, and not 1 is 0. So if I'm using NOR, you can see that 1 NOR 0 will give me 0. Why? Because 1 plus 0 is 1, and not 1 is 0. So in conclusion, NAND represents complement of AND, and NOR represents the complement of OR. And we may go more details on this in the next lectures. So let's see one exercise example here. Here, the same thing as the previous examples we saw. It's a sum of product expansion. So the first question said we should find the sum of product expansion of these Boolean functions. Here we solve it using the Boolean identity, but also if you want, you can use the truth table. If I'm using the truth table, I have only SY. So the possible combination will be 4. 0, 0, 1, 0, 1, 0, 1, 1, 1. Then based on the expression here, I'll find the S invert. If it's 0, it will be 1. 1 plus 0 is 1. And then 0 plus 0, if it's 1 is 0. So you just, again, develop the truth table. Then anywhere you have the expression S invert plus 1 is, the solution is 1, then you write the term down. As we saw in the example, if it's X, if it's 0, then it will be S invert. If it's 1, then it will be X. But here we solve it using the Boolean identity. So since I have S invert plus Y, I have only 2 terms. So I'm missing Y in the first term, and I'm missing S in the second term. So what I did, I used the unit property. This multiply by 1, multiply by 1. Then I know that the 1 here, I can change it as S invert plus X. The 1 multiplied by S invert, I can change it to Y plus Y invert, because I'm missing Y at the first term and I'm missing S at the second term. And that's what we did here. So first thing we say S invert times Y plus Y invert times 1. And 1 is the same as Y plus Y invert. And then the second one also we use S plus S invert. As we said, we have Y. So we are missing the invert, the X. We have X, we are missing Y. So that's why we use Y plus Y invert for S invert. Then the second one, we use S plus S invert for Y. So when we open the expression here, we are going to get S invert Y plus S invert Y invert plus XY plus S invert Y. Then we're going to use the commutative and also the idempotent law to remove the last term. So our answer will be, the first one is okay, S invert Y, we have that. The second one also is okay, S invert Y invert, we have that. And the third one will be X, Y. The idempotent law will exclude the Y, S invert. So here we can see we have a sum of products. In this case, it's two terms, so we have two terms. The second question said we should find the same thing, sum of product expansion for X, Y invert. So what is the answer? This is already in the sum of products because it's one term. And we have S, Y invert, so it's a tricky question. It's already sum of products. And if you make the truth table, you see that you get only one in the truth table, only one row as one in the truth table, and it should be X is 1, Y is 0. So let's see the C. C also, we're going to write a sum of product for F, function F at X, Y. So here in the C, we have 1. So here we say that we need to write a sum of all products, the sum of all products of the 10. So the answer will be, what is the possible combination? And we have 1, 1, 1, 0, 0, 1, 0, 0. So that's what we have, 4 terms. If, for example, it was F at X, Y, Z, then we're going to have a possible of 8 possible combination. So we're going to have, for example, SSS, S invert, Y invert, S, Z, etc. So the possible, since this is 1, it means the whole combination is 1, 1, 1 throughout. So that's why we cannot eliminate any of the terms. So the answer with the possible combination of two variables, we have 1, 1, 1, 0, 0, 1, 0, 0. Then we had all the 10. The next one, we have the Y invert. So this is the same as the first question part here. Since we have Y invert here, we can say F at S equal to 1 times what? The Y invert. We had 1, it's same as we had multiply 1 here or multiply 1 with the S invert. Here we use the identity, multiply Y invert by 1. Then we get X invert plus X, and that's what we have here. Then we open the parentheses, so we get XY plus SY and S invert Y. Again, this is why here we can't use that. Even if we use identity, we will come to the same one. Because if I multiply 1 by 1, and we say 1 is X invert plus Y, or Y invert plus Y, S invert plus X, and the term will be the same. So you here to be the whole 4 possible terms. By here, we know we multiply by 1. We are missing X, so we use multiply by S plus S invert. So let's see the second question. Here they say we should find the sum of product expansion of the Boolean function. So the same question, which equal to 1 if and only if S equal to 0. So A, we said that we need to write all the terms that have S invert in them because S equal to 0. So here we get S invert. This is a 3 variables, S, Y, Z. We said it's equal to 1 if only S is 0. So write all the term that X is invert or S is 0. So the possible will be 4 of them because this is 3. The possible combination of 3 variables is 8. What I mean is that 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, all the possible. So if that is the case, you will see that if we look at the truth table, we can go back 1 second and look the truth table. There was an example. Yes, so this is the example. 3 variables, S, Y, Z. So the possible combination is 8 rows. How many 4s S we have? 4. We know this is Boolean, so the S variable can be only 1 or 0. We have 4 ones, and also 4 zeros. So that's why here our question said, let's go, when s equal to 0. So when s equal to 0, the possible combination is only 4. So that's why we write it down. And we write the whole term down. So let's go back again. So when s is 0, so when s is 0, I have s invert, y, and z. S invert, y, and z invert. S invert, y invert, and z. Then S invert, y invert, and z invert. And that's what we have as a solution here. So we have 4 terms, sum of product. Now the second B said when sy equal to 0. And the same concept again. Here we need to write all the terms that include either x invert or y invert. So in this case, when s is 0 and when y is 0. So when we look at the truth table, the same thing. The possible, we can see here we have y is 0, y is 0 here, s is 0, s is 0 here, s is 0, and y is 0 with s is y is 0. So here when s times y is 0 means both s and y, either one will be 0 or both of them will be 0. So when we look at the term, you can see the first term is only when y is 0. The second term is only when y is 0. The third term is when s is 0. The fourth is when s is 0 again. But the fifth and sixth is when both s and y is 0. Again, if we go back to the truth table, we will see the same. Then the next is when s plus y equal to 0. So here we need to include all the terms that are both s and y equal to 0, because you see when x or s times y equal to 0 means when one of them is 0, what we mean is that 1 times 0 is 0. 1 times 1 is 1. We don't need it. 0 times 1 is 0. 0 times 0 is 0. So here we have to look for all the terms that 0 times 0, s is 1, y is 0. Or y is 1 while s is 0. Or both of them are 0. Then this condition is true. But when we have s plus 1, the only time it will be 0 is when both of them are 0. So when s is 1 and y is 0, the answer will be 1. So we don't need a term where we have, for example, let's go back to the B answer. For example, the term x, y invert, and z, it won't give me 0 if it's plus, if it's s plus y is 0. It will give me 1 because s is 1. 1 plus 0. So again, that's the whole concept. So you can see the answer here will be only when both are 0. So when s is 0, y is 0, z, then s is 0, y is 0, and z is 0. It doesn't matter. Z can be 1 or 0, it doesn't matter. But when we look at the truth table, it's only 2 rows that will have both x and y 0 at the same time. Then the last question, saying that now all the terms have to be 0. But luckily, this is multiplication, it's not addition. If this is addition, then we are going to have only one term, and the term will be x invert, y invert, and z invert. But here, we are going to get somewhere around like 6 or 7. Actually, we're going to get almost all the, 1, 1, 1 will be excluded. Because when s is 1, y is 1, z is 1, the answer will be 1. Apart from that, if all of them are 0, or only 1 is 0, or only 2 is 0, we get 0. So here we can see we count the term 1, 2, 3, 4, 5, 6, 7, all the 10. And what I mean is that, let's go back to the table here. You can see that here, we said that we want to find the sum of product expansion when s times y times z equal to what? 0. When s is 1, y is 1, z is 1, the answer will not give us 0, it will give us 1. So we don't need that. Apart from that, the rest all will give us 0. Because at least we can see 1, 1, 0, 1 times 1 times 0 is 0, 1 times 0 times 1 is 0, 1 times 0, 0 is 0, 0 times 1. Anytime we have 0, 1, 0, the answer will be 0, or all of them 0 or 2, 0. So that's why, again, the solution, we have all the 7 terms. The only term we removed was when x and y and z, both, all the 3 terms are 1. So let's say the next question here says we should express each of these Boolean functions using the operators, only 2 operators, the product and also the complement. So which means if we have a plus, we want to see only product and complement. And I think this question is only one rules we have to use, De Morgan rule. Since I need only product or invert, if I have x plus y plus z, I'm going to invert everything using the De Morgan rule. And the answer will be s invert times y invert times z invert. So we can see A here. We have s plus y plus z. We invert everything. And later on, we will see that we get x invert times y invert times z invert or invert. Then we have B, s plus y invert plus s invert plus z. So here, since we have a parenthesis, we will start with the inner parenthesis first. So you can see that we inverted everything. And secondly, inverted the parenthesis first in the inner parenthesis. Then secondly, we invert everything. But to make it accurate, you can see that we also invert x because you have to be twice, so outside. Then this is the same as writing x invert, y invert, we invert z invert, so separately, s and y as x times z. So plus invert will be, again, multiplication. So all these questions, we are using the Morgan theory. And when we look at C also, we have to change this to plus. So we remove the invert. We get S invert times Y invert invert, which will give us invert invert will give us, they will cancel. So our answer will be S invert Y. The same thing applied to D. D, we can invert, and we have only one parenthesis. So we can invert everything. We shouldn't invert including the X now, because if you invert the S, you create an addition here. We don't need addition. The expression have to be only product and invert. So we invert them. So you can see the solution. We invert the parentheses and we invert it twice, because here we didn't invert this. So it's like invert and invert. It's like you didn't invert. So you invert twice. The same concept here. Since we don't want to invert this multiplication, otherwise it will be plus, we have to invert this twice. And invert is the same as y invert y by itself. So here also we have some few theory on the sum of product. Here we say that all equations can be written in a sum of product. And also each row is called a midterm, sum of product. So a midterm is a product n of letters. Each midterm is true, which means the midterm have to be, the function row have to be 1 for that row and only that row. So from there we can form function by Horing means by summing the midterms. So we saw the example, for example, sy plus s invert y. Horing means sum of the 2 midterms, so sum of the midterms, where the output is true. And it's output true means where the function output is 1. When it's 0, we can't do anything. So here they give us example of 2 variables a, b, f at a, b. The possible combination is 0, 0, 0, 1, 1, 0, 1, 1. And you can see our output from the function is 0, 1, 0, 1. So this means we have 2 terms. Our 2 terms here, a is 0, so it's a invert, then b. The last one, a is 1, b is 1, so it's ab. So our solution will be a invert b plus ab. And that's what we have here. A invert b plus ab, because that's only the row that we have 1 for the output function y. We also have previously we just doing only the sum of products, which we went through the first time also. But we also have a product of sum. The product of sum, each term, we call the each term mass term. So you can say, instead of saying A times B plus A plus, times B, which is the sum of product, this time we say A plus B times A plus B invert, which is what? Product. We have product now. The solution is product of two sums. So this is called the product of sum. And each term plus is called the mass term. The mean term is for the product. And the mass term is for. And the same concept now is opposite. So let's go through the rules here. We say that all Boolean equation can be written in product of sum instead of sum of product. But now we call each row as the mass term. The mass term is again the sum or of literals. Now each mass term is false. So remember, in the sum of product, we say that each mean term is true, is 1. But with the mass term, we write the output when in the output term when the answer is 0 instead of when it's 1. 1 is for sum of product. Product of sum is 0. So each mass term is false for that row and only that row. Form function by ending. Ending means multiplying the mass term for which the output is false. So the example again, previous example, now you can see we are circling the zeros. Y is 0 and Y is 0 here. So the mass term here will be A invert plus B invert because they are 0, 0. And then here we get 0, 1 is 1, 0. So it will be A invert plus B. So here they say you are going to a cafeteria for lunch. You won't eat lunch, represent E. Or if it's not open, represent O. And if only serve corn dogs, which is C. Now we want to write a truth table based on this condition here. So write a truth table for determining if you will eat lunch. And when we look at the term here, they say you won't eat lunch, which will be our output. If it's not open, so if it's not open, it means it's 0. And also if they only serve corn dogs, that means it's 0. So I will eat, I will not eat. And if one of them is 0, 1 also is 0. But if I will eat, if it's open or corn dogs, that's 1. So based on the condition here, we have 0, 0, 1, 0. Here, they don't have to have both. We are using the term or this. So if it's open and also they don't serve corn dogs, then it's also 0. So to write a sum of product, remember we have to have 1. And the output have to be 1 sum of products, which is the midterm. So we get only 0 C invert. Now to write the product of sum, we need 3 zeros. So we have 3 zeros, 1, 2, 3. And we have to write them also. Simplified Boolean expression, we have AB plus AB invert. And we can say that if I have AB plus A invert B, we have a common B, so I take the B out and I'll get A plus A invert. A plus A invert is 1, so the answer will be B. Again, the invert here is for A, so we have AB plus A invert B. So the common term here will be B. Then we get A plus A invert. A plus A invert is the unique property, which is 1. The answer is B. Second example, we have AB plus ABC. So we have to use the distributive property first. So here we say A, B, and we have the AB, because AB is here, AB is here. So we represent AB as 1 plus C. So AB 1, 1 plus C will give me 1. Because if C is 0, the answer is 1. If C is 1, the answer is still 1. And then AB1 will give me AB. Then A times A will give me A. So AAB, we get AB. So this will be the conclusion of our lectures on Boolean algebra. And also the concept here we learn is the sum of products. And also at the end, we did 1 or 2 examples for the product of sum. In product of sum, we call the terms mass terms. Sum of product, we call the term mean term. We only write down the expression when the function is 1 for sum of products. For product of sum, we write the term down when the function output is 0. So again, this will lead us to logic gates now, which will be our next lecture. Thank you. Bye.